Hey guys, this is Miss Bufford, and in this video, we're going to talk about types of chemical reactions. Your learning goals for this video are to review the 5 indications that a chemical reaction has occurred, learn the parts of a chemical equation, identify types of reactions, and use the activity series to predict the reactivity of chemical reactions. So first, we're going to review some evidence that a chemical reaction has taken place. We've learned this previously last semester in our matter unit, but we're going to just have a quick reminder so that we can have this fresh in our mind when we're trying to identify some reactions. Temperature change is one indication that a chemical reaction has taken place. If we have something getting hotter or colder and we're not necessarily trying to heat it or cool it down using external forces, then that is an indication that a chemical reaction is taking place. A color change is also another indication. Bubbles being produced. So remember, if we're not trying to boil something, but we're mixing things together and we can see bubbles being produced in the container, that is gas that's being formed, and so that's an indication of a chemical reaction. The formation of a precipitate in a solution. So sometimes when we mix two solutions together, they'll form a cloudy substance, and that cloudy substance is actually little tiny solid particles of a new substance that are precipitating or just coming out of solution because that new substance that's being formed is no longer soluble. And then production of sound and or light is also evidence of a chemical reaction. All right, so now let's go ahead and take a look at the anatomy of a chemical equation. We've seen some chemical equations before, but we're going to go ahead and go over the parts of the equation as a whole. So in a chemical equation, we have reactants here on our left side at the beginning, and this is separated from the products by a little arrow here in between, and the products are always going to be on the right side of that arrow. So our reactants are the starting materials for the reaction. So this is what we have before we mix them together and get the chemical reaction starting. And then our products are what are formed during the reaction. So that's what's left after the reaction has come to completion. And then if we take a look here, we've got some little letters in parentheses after each one of these substances in this reaction. And those are just giving us more information about the state of matter that those substances are in. AQ stands for aqueous solution, which means dissolved in water. And if you see an S, that means that that is a solid at room temperature. And then we might also see an L for liquid or a G for gas in those little parentheses sometimes. When we're reading a chemical equation, we read this and sign, or I'm sorry, these plus signs as and. So sodium chloride and or reacts with silver nitrate to form or yield or produce silver chloride and sodium nitrate. All right. And then one other thing I'd like to point out is the use of coefficients. And we've seen coefficients before. We talked about them when we talked about chemical formulas. But coefficients are actually going to be very useful to us going forward. And they tell us how many units or how many molecules we have for the substances that are listed directly behind those coefficients. So in this case, we have, you can see on our reactant side, we have 2 hydrogen molecules. And on our product side, we have 2 water molecules. All right. So now let's go ahead and talk about the different types of reactions. And I've gone ahead and separated these into oxidation reduction reactions, which are also called redox reactions for short, or double replacement, also known as sometimes as ion swap reactions. And we're going to go ahead and start by talking about the double replacement or the ion swap reactions first. There are 2 types of double replacement reactions that we're going to talk about, where we will discuss acid-base neutralization and precipitation reactions when we talk about these. But basically, an ion swap reaction or double replacement reaction occurs when 2 chemical compounds swap ions with one another. And so they have to be ionic substances in order for them to swap ions. But the main thing here is that there's the main thing that differentiates double replacement or ion swap reactions from the redox reactions is that there's no exchange of electrons. Everyone keeps the electrons they have, they just trade partners, all right? So in a redox reaction, there's actually movement of electrons between the chemical species, and we'll talk more about that later. But here in double replacement, it's just ions trading partners with each other. So you can think about it as maybe they're doing the do-si-do. So in this ionic compound, we can just assume that A would be the cation and B would be the anion. And here C would be the cation and D would be the anion, because remember, we always list our cations first in our chemical formulas. And you can see that this arrow over here is saying that A is going to come over here and react with D, and that C is going to come over here and react with B. My red arrows are my big red arrows are kind of off a little bit. But they end up trading partners, and so we end up with compound CB and compound AD. Right, so that's the main idea of double replacement. So let's take a closer look. So the first type of double replacement reaction that we're going to talk about is the acid-base neutralization reactions. And these neutralization reactions, an acid is a compound that has the ability to produce an abundance of hydrogen ions when it's dissolved in water. And that, in this case, would be this compound right here. This is hydrochloric acid. If we were to dissolve this in water, it would form hydrogen plus or H plus ions and chloride ions. All right. And a base has an abundance or can produce an abundance of hydroxide ions when it's dissolved in water. And so this right here is going to be our base. So here I'll acid and base. Because when this is dissolved in water, we produce sodium ions and hydroxide ions, right? So anytime we do a double replacement reaction, these are going to be occurring in liquid aqueous solution. And so when that happens, when we dissolve these ionic substances in water, they come apart and they form these independently floating ions in water. And what happens in a acid-base neutralization reaction is that these hydrogen ions are going to come over here and they're going to react with the hydroxide ions, and they will form water, H2O. And then sodium and chloride ions are going to come together and they're going to form an ionic compound. And in this case, it happens to be table salt, sodium chloride. But when we say an ionic salt, any ionic compound, if it's not dissolved in water, is an ionic salt, right? It forms a crystalline solid substance. And so any ionic compound, we can use the term salt to describe, right? So an acid-base neutralization reaction always forms water and some kind of ionic salt. And that's how we can identify them, is by the products and by looking at the chemical formulas of the reactants and saying, oh, that's a hydrogen right there in front, and oh, there's my hydroxide. That's an acid-base neutralization reaction. All right, the second type of double replacement reaction that we're going to talk about is a precipitation reaction. In precipitation reactions, two ionic compounds are each dissolved in water, and when the two solutions are combined, a newly formed non-soluble, that's the big key here, is non-soluble product will begin to precipitate out of solution. And this happens because that new product that's formed is just not soluble. So it can't stay in aqueous solution. So visually, if you were looking at these reactions, you would be able to tell that it's a precipitation reaction because you have the formation of that substance that makes your mixture cloudy. These are pictures at the very beginning before they disperse throughout the whole solution, making it just cloudy, but that is what it would look like. But if you don't know what it would look like, if you can't see the actual reaction and all you have is the equation, then you can identify this as a double replacement precipitation reaction by identifying or by using the state of matter to determine whether a new product was formed or not. All right, so we can first look at this and say this is definitely a double replacement. We've got two compounds here and two new compounds here. And I can definitely clearly see that cobalt is going to come over here and react with hydroxide to form cobalt hydroxide. and that sodium is going to come over here and react with nitrate to form sodium nitrate. All right, so double replacement for sure. And if I'm not sure about precipitation or acid base, then I have to look over here. Yes, I have hydroxide, but there's no hydrogen coming from this compound, so that can't be acid base. But I do have a solid forming as a product, and so that is definitely going to be a precipitation reaction because I will get the formation of cobalt hydroxide in my test tube or my mixture wherever I'm mixing this. All right, so as long as I have an insoluble solid product, that is going to be precipitation. All right, so now we're done talking about double replacement reactions, and we can start talking about the oxidation reduction or redox reactions. So in a redox reaction, there is movement or transfer of electrons from one chemical species to another during a chemical reaction. And by chemical species, I just mean either an element by itself or an ion or just something. All right, so there's 4 different types of redox reactions that we need to be able to identify. We've got synthesis, decomposition, combustion, and single replacement. So let's go ahead and talk about synthesis first. A synthesis reaction is where we take a couple different things and we combine them to form one product. So in this first example, I've got magnesium and nitrogen combining to form magnesium nitride. And in the second example, I've got calcium and oxygen coming together to form molecules of calcium oxide. So even though I have 2 molecules here, they're still the same substance. And the idea is that we're taking 2 different substances and combining them to make a single substance. And that is going to be a synthesis reaction. If you think about it, the word synthesis is to make something or to put things together. And that's what we're doing here. All right, the next type of redox reaction is a decomposition reaction. And in a decomposition reaction, it's basically the opposite of a synthesis reaction. We're taking one chemical substance and we're breaking it apart into simpler substances. So for example, we're taking water molecules here and we're splitting them into hydrogen gas and oxygen gas. So that would be an example of a decomposition reaction. All right, this next one is combustion reactions. And a combustion reaction, we've got a hydrocarbon, which is any compound that contains carbon and hydrogen. They don't always have to be just CH4. It could be C12H, 20 something. All right, hydrocarbons come in a variety of combinations. All right, so we've got our hydrocarbon. It has to react with oxygen gas, and it has to produce at least carbon dioxide and water. Depending on the identity of the hydrocarbon, you might end up with a third product too. But the main idea for identifying a combustion reaction is that we've got a hydrocarbon, oxygen combining or burning together to produce carbon dioxide and water. And that's how we identify a combustion reaction. All right, and this next one that we're going to talk about is a single replacement reaction. And this is the last type of redox reaction that we're going to learn about. And in this type of reaction, one element in a compound is replaced by another element. So this could take the form as metals replacing other metal ions in a compound, or a non-metal coming along and replacing another non-metal ion in a compound. And it's similar to double replacement, only we don't have 2 compounds. We have a single element by itself and one compound, all right? So we've got our single element here and then this compound here, and you can see that this is trading places and going over here for this one right here. All right, so let's take a closer look. We can actually predict whether a single replacement reaction is going to occur or not, and we use something called an activity series. Right, and the activity series this is basically a list of metals, and up at the top are the most reactive metals, and as we move down, the metals get less and less reactive, so the decreasing reactivity as we move down that table. But basically, this is the example for the metals replacing metals here. If we take a look down here, I've got this compound where we've got iron and chlorine in a compound together. And if we add calcium to that, we have to determine whether that's actually really going to happen or not. And we're going to use the activity series to do that. So if I take a look here at this compound, I've got iron as my metal here. So here's iron on the activity series. And I'm trying to see if calcium is strong enough to replace it. Calcium is located right up here. And the main rule that you want to keep in mind is that the more reactive element or more reactive metal is always going to end up in the compound. So if calcium is more reactive than iron, then it is going to be in that compound with chlorine instead of iron. It's going to displace iron. And that happens to be the case. So since calcium, you can think of calcium as having bigger muscles than iron, it says, give me that chlorine, and it takes chlorine, and iron's left all by itself then. And then off calcium goes with chlorine. All right, so that's how we use this to predict the products of a single replacement reaction. Just always want to remember this most important rule is that the more reactive element will replace the less reactive element in compounds. All right, so knowing that, let's go ahead and see if we can answer this tricky question. If iron reacts with water and oxygen in the air to form iron oxide, which we all know is rust, and stainless steel is mostly iron, why doesn't stainless steel rust? Right, so I want you to go ahead and pause the video for a minute, take a look at the composition of stainless steel and the activity series, and see if you can come up with a reasonable answer for why stainless steel doesn't rust if it's mostly iron. All right, so hopefully you had a chance to pause the video and you had a little bit of a think about this for a minute. But let's go ahead and start by taking a look at the composition of this stainless steel. So stainless steel is an alloy. It's a mixture of a bunch of metals, and there's even some other stuff in there that's not metal. For example, we've got iron, molybdenum, nickel, chromium, sulfur, phosphorus, silicon, manganese, and carbon. That's a long ingredient list for stainless steel. But we're more concerned with the metals that are in here. So we've got iron, manganese, chromium, nickel, and molybdenum. Molybdenum is actually not on the activity series, so we're going to kind of ignore that. But we want to at least take a look at where all the other metals are located in the activity series. So I've got iron here. Here's iron. Nickel is right here. Chromium is right here. And manganese is right here. So if you take a close look, then you'll notice that manganese and chromium are higher up on that list than iron is, meaning they're more reactive. There is not a whole lot of manganese in this stainless steel, but there is a sizable amount of chromium. And because these two metals, mainly the chromium, are more reactive than iron, they are actually beating iron to the punch when they're trying to react with the oxygen in the air. And so chromium in this stainless steel does react with the oxygen in the air, and it forms something called chromium oxide. And that chromium oxide is it's called a passive tarnish, which means that unlike rust is more of an aggressive tarnish where it will degrade the metal over time. But chromium oxide is a passive tarnish and actually works as a protective layer over that stainless steel to keep the oxygen in the air from reacting with the iron that's in that stainless steel mixture. And so you can kind of, in a way, think of stainless steel as one of those self-healing materials. Not to say that it would get rid of any scratches, but it actually, by informing this chromium oxide layer on the outside, is protecting itself. And anytime it were to get scratched, then that chromium would still beat that iron in reacting with that oxygen. All right, so that's just kind of something cool to know. The last thing that we want to talk about with single replacement reactions is that they can occur with nonmetals as well. And just in order to predict the outcome of a single replacement reaction involving nonmetals that switch places, you just follow the same rules about reactivity. You just have to look at the periodic table to be able to see which one is more reactive than the other. For example, chlorine will replace anything below it in its group, but it can never replace fluorine because fluorine is more reactive than chlorine. All right, So now let's go ahead and practice what we've learned in this video. I would like you to go ahead and pause the video for a minute and see if you can identify these different types of reactions based on what we've talked about. And we'll come back and talk about it in just a second. All right, so hopefully you had a few minutes to pause the video and try to identify these reactions. This is going to be something that you're going to have to do on the test. So let's go ahead and talk about them. This first reaction right here is going to be double replacement. And so we've got two compounds on the reactant side and two new compounds on the product side. So that's our kind of first giveaway that it's going to be double replacement because we've got four different compounds. And it's not going to, let's go ahead and see if we can identify which type of double replacement it's going to be. Oops, I accidentally hit the screen a little bit too early. It's definitely not acid-base, and it would be hard for you to say precipitation because I didn't actually give you the information that you would need, but potassium phosphate is an insoluble product, so it will form a solid. So if you said precipitation, even if it was just a guess, bonus points for you, but it's definitely double replacement. All right, so the second equation is going to be a combustion reaction. So combustion, because we've got our hydrocarbon here reacting with oxygen, and it produces carbon dioxide and water. So those are the telltale signs of a combustion reaction. Always going to have oxygen, always going to have carbon dioxide and water as a product. All right, the third equation down here, that's going to be single replacement because we've got lead by itself here, and then we've got iron sulfate, and those are going to react and form lead sulfate, and then iron is now going to be by itself. So lead displaced iron in this reaction. All right, the fourth equation is going to be decomposition because we are starting with one chemical substance, and that is breaking down into two other smaller chemical substances. And then the fifth equation here is a synthesis reaction because we're combining two things to make one product. And the last equation here is going to be double replacement, but this time it's going to be an acid-base neutralization reaction. And so it's double replacement. We've got four different compounds here, and acid-base because we have hydroxide ions being produced when this is dissolved in water and hydrogen ions being produced when that's in water, and it's producing water and an ionic salt. Right? So hopefully this video was helpful. If you guys have any questions, please feel free to ask during class. I'm happy to help you, and I will see you then. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.